Hi everyone, welcome. I guess we are like 2 minutes before we're starting, so we're gonna wait for everybody to join in. But thank you for joining today. I'm excited to do this. Let me know if you guys can hear me clearly. Hi everyone, welcome to today's session. This is week 2 of our 6-week webinar on Introduction to NLP. I'm super excited that you all are here. Hopefully you can hear me correctly. All the panel members are also here, so please do ask the questions that you have throughout the session in the chat section and the Q&A section. And we're going to try and answer as much as we can. I guess I'm going to give it like another minute and then we're going to get started. Great, I see we have a lot of people from different places. Very excited. Thank you for joining. So great. Let's get started. A quick introduction about myself. Hi, my name is Jayeeta. I work as a senior data scientist for Intelligent US. We are based out of New York City, and like it's been a great honor organizing this along with WWCode Data Science and bringing this webinar to all of you. So I'm super excited to get started. I guess let's start and go through it all. So for the week 2, we are gonna take a deep into some of the feature engineering techniques of natural language processing. Last week, we did a lot of NLP 101 where we understood what are the pre-processing that we need to do. So we take a deeper, take a little bit of look at the underlying math and we go from there. But before that, I guess thank you to all the other panelist members. They have like really volunteered and an amazing work putting together this series. Rishika did an amazing job last week as a speaker, and all the leaders are present in the chat. So thank you for all of them for their support, and I look forward to the rest of the series as well. Before that, thank you to our sponsors as well. Thank Home Depot for putting together this much needed events for the community. So if you guys are active in Twitter, Instagram, wherever, do show your appreciation by retweeting your post. Helena, one of our panelist member, would be sharing them out in the chat. And let's start. So before we begin, I guess you'll also have the link to the slides in the chat section. So do access to it and you can go along with how we discuss and go through it. If you have any questions, please feel free to ask in the Q&A box and the panelists will take them up. So let's start. So what is feature engineering? We're gonna take a look at some of the very key areas, which is very important in order to make sure that we have a very holistic NLP model and we are doing everything right, doing all the noise cleaning, making sure the data that we have is very clean and starting our model from a very, a good baseline. So this is the agenda for today. Some of the topics may feel a little familiar from last week. There's definitely going to be a little bit overlap, but we're going to do a little bit of deep diving for each of these topics, see what are their background or the underlying math with it. So let me know if you have any questions or you want me to repeat anything, and I can do that again. A quick recap from last week. I guess some of the questions we answered is what is NLP? It's like a combination of a lot of fields. There's ML, there's AI. NLP combines a lot of those fields, but also has a very unique nuance to it because we are working with kind of text data, which is very different from the kind of data that we usually use for machine learning, which is mostly quantitative and not qualitative. Where we are utilizing sentiment analysis is one of the big area where we are trying to utilize text data, reviews from Amazon, Yelp, any kind of those feedbacks, and trying to analyze of how we can or how we can engage people's emotion about what they feel about the product or the services that the companies provide. Challenges. I'm a Big Bang Theory fan, so this image like really resonates with me. So what we are trying to say here is language is difficult. It has nuanced intents. When a person talks in a general language, human brains can do a very quick intent classification and understand if it's sarcasm or a literal translation, but it's very difficult for ML algorithms to do such. So that's why we say that we need to handle the initial data cleaning very carefully. And that's why what we must do is pre-processing. So yeah, clean all the data. Rishika had went through some of the features. You can go back to the recordings and the code and look over that. So what is feature engineering? So basically what we can, how we can define feature engineering as it's a process of kind of selecting and transforming some of the variables that we have had and creating a model or any machine learning system or a method which includes all those kinds of data, applying some rules and also a lot of judgment. So feature engineering is not only based on hard and fast rules, but you have to understand the data through and through. You have to define what's good for your model or what you're trying to finally predict. So it kind of depends upon a lot on the result or the final outcome that you're trying to achieve. So it's feature engineering is also a big part, that a big chunk inside pre-processing. So let's go over it a little bit. So why do we need feature engineering? Basically, the ML algorithms cannot work on raw text data, right? So we humans can understand raw text, but what they can understand is only numeric representation of an actual text. So how do you numerically represent a text? You kind of vectorize it. And that's where the concept of matrix vectorization comes in. The technique that even Rishika showed last week is like one hot word representations. So the way that we can do that is like, if you see the example here, that there are this sentence, the cat sat on a mat, like we are trying to gauge that between a sentence where other words are matching up. So you would see one exist for the same match words that are aligned with each other, and for the rest of it, it's zero. That means it do not exist. So in that way, we are telling the machine which of the words are available in a sentence that we are passing in the model or in the text that we're trying to analyze, and which do not. So it's like a kind of a binary one-hot representations that we do. We'll also talk about some of the popular methods of feature extraction like bag of words and TF-IDF, but we would do this in next week's session. Today we will look, so before going to that, I just wanted to give you a quick example. Like think of it like if you want to buy a house, like there are so many features that you would consider, right? Like what's the average number of rooms in the houses? So that becomes one feature. If you go and look at the Boston housing data set, it's like a very standard data set for any ML problem. We would see that these are some of the features that we utilize in doing the model. So we would also consider what's the crime rate in the area, what's the business, like how many businesses are there, what's the accessibility to highways and railroads. So those are kinds of very important features in order to predict the price of a particular house in a locality. So just to give you a very, real life example so that we are like in a same platform and understanding what features are we talking about here. Now, what is the feature for now NLP areas? So there are multiple ways we can understand it. But before that, we need to understand what's syntax and semantics. So when we talk about syntax, it's just the way, like, I'm just going to go ahead one slide and come back to the previous slide. So syntax is the grammatical structure of the text, and semantics is basically the meaning that's conveyed in the text. In the image, if you see, it's very funny. It says that, oh, call me a cab, but it says, okay, you are a cab, like as if I'm saying that call me a cab and my name is a cab. So even though it's syntactically correct, it may not be semantically correct. So they are kind of codependent. So going back to the previous slide, so that's where they are codependent. So a set of specific rules, conventions, and principle kind of govern how the way words are combined. If it's not in a correct structure, a combination of words would mean nothing to us. So the next step is like English language has multiple constituents. Some of them are like called words, phrases, clauses, and like a combination of everything is like called sentences. So going forward, if you see the second point of it, how it says that what we discussed just earlier, like some of the sentences can be syntactically correct, but it may not be semantically correct. The example that I wanted to show here is funny. It says that the cats flow supremely. So if you do a grammatical analysis of this sentence, it has a subject, it has a verb, and it also has that verb. So it completely makes sense grammatically, but it do not make sense semantically, but it doesn't, because it doesn't mean anything. So so there's a lot of combination of linguistic heuristics and the whole process of the grammar that we need to understand in order to make that make sense. So feature engineering for text. Let's see what are some of the steps that we can do in order to achieve it. This is something that we discussed last week, part of speech tagging, but I wanted to go a little bit deeper and discuss with you how we achieve, or how we get to that point of actually tagging it. So it's also called grammatical tagging, or like word category disambiguation. It's kind of process of marking up like which words or which text in a corpus corresponds to which particular part of speech. It has to match both its definition as well as context, right? Because tagging is like kind of a classification, and it may be defined as like an automatic assignment of description, but that descriptor, that the tag, which is like a kind of a representation of both its part of speech from the context as well as the semantic information that it's trying to explain, right? So this is definitely not like perfect solution. Like we still have like a work going on, and we're trying to improve it day by day, because we know that language has so much nuance, and we want to cover our grounds as much as possible and include as much as context into it in order to ensure that our accuracy is high. So in this example, if you see that the text says that Bob made a book collector happy, and the sorry, I'm hearing a little bit of background echo. Yeah, thank you for that. Sorry for that. Yeah, so in this sentence, if you see that Bob made a book collector happy the other day, how are we breaking it down? So Bob kinds of becomes a subject. There's another layer to tagging part of speech tags. You can also identify subject, object, and verbs that comes into the whole picture, so that you can break down the sentence in a much meaningful way of which way it's getting accepted, if you understand what I mean. So Bob is like a subject, and here made is like a verb. But when you look at a book collector, it's an object, but it's a compound noun. So it's basically kinds of trying to break down the whole compound noun and saying that this is my part of the sentence which the subject is applying or referring to, but that may or may not be a only single word. So that's why the layering of it also has a lot of nuance to it that needs to be carefully understood. So, but the another aspect of this analysis is that the tags reveal a lot about the word and its neighbor. So you can say that knowing whether a word is a noun or a verb kind of like not, it's not 100% accurate, but kind of tells us like what are the likely neighboring words they might have. So like say nouns, if it's preceded by a determiners and adjectives, then we can assume that maybe a verb will have a noun next to it, because that's kind of going to be like an object of the whole subject verb object sentence. Going forward, so why do you think that we need POS tagging? The first answer to that is like the ultimate goal that we need to solve the word sense disambiguation. Like we do not want multi-contextual words to mean different and getting vectorized differently. So if you look at this example, it's very intuitive. Like you see the same sentence has three different meanings if we explained it in a different way. First one talks about like time flies like an arrow, where time is the noun, and it says that it's flying like an arrow. So like an arrow becomes a a phrase. But in the last one, when you see that it's like time flies like a arrow, so you're asking that you are like you time here is a verb because you're asking it to time it, like it's a action or a work word that you're implying, and then you're saying that time the fly, which is like going like an arrow. So there is the way that we could achieve it is depends on a lot about the more and more context we can include in each of these methodologies. And if you want to understand where it's used, a lot of it is used in information retrieval, text to speech. Like we need to understand if a object is a noun or a verb, like only then we could be able to transfer it in a very correct format, and also in machine translation. So that's why it's definitely a great area of research that's still going on, and but it's kind of like a prerequisite to all our different problems that we need to solve, but that we need to achieve, even though it's like not 100% accurate for any case. So this is just to understand the methods of the POS tagging. I'll not go too deep, but I just wanted to walk you all through some of the major areas that it is being done, and still it's being, the research is going on in all these domains. So rule-based POS tagging is basically, we are using contextual information to assign tags, and it's kind of manual. There are a lot of linguistic domain SMEs or subject matter experts that comes in and then understand the text and then kind of does that manual annotations. That is time consuming, it's not scalable, but it was like one of the initial ways we started. Like example of a rule you can see here is that if an ambiguous word X is preceded by a determiner and followed by a noun, then we need to tag it as an adjective. It can only work so far, and it would not consider a lot of options, and it's definitely not scalable. Great. The next is like transformation based tagging. So if you think about it, think of transformation based as like kind of a semi-supervised model. So here we have like two-part rule where we have like one condition, the trigger, and possibly we already have a current tag. So like somebody has already manually QA'd and did a little bit of tagging on that, and then we pass those tags through a rule. Like if you can see the current classification, it goes to the learner and tries to say that, is it the correct tag? Is it what we have tagged? Or if it's not, then according to the rule that we have passed it through, it gets changed and a new tag comes through. So that the trigger function is kind of doing the transformation and changing the tag X to Y depending on the rules that we are passing it through. And the next one is like stochastic probabilistic tagging. This is a way of, kind of doing a probability score of seeing that what tags occur with which words. Some of the initial work was started by using Brown corpus, which has like 1 million words. And a lot of work has been done by utilizing the hidden Markov model. We're going to just touch upon the concept a little bit, but before that, let's see what are the challenges. Like we as discussed, the tags are not generic. So problem is with the ambiguity, and a single word can have different tags in different sentences based on like different context. Let's look at this example. Like it says that she saw a bear, and bear here is noun because it's like an animal, and then it says that your efforts will bear fruit. Here bear is like a verb, that you're doing all this effort and it'll get you a good result. Another example is like the trash can is hard to find. Here can is a noun because it's like a an object, and then I can do better, and I can here is like a modal verb that I know it's I can. So it's easier for like humans to understand these differences, but how do we teach the machines to understand this nuanced differences? So, and that's why we say that retrieving POS tags have two components. Like individual words have kind of a statistical preference that which word might be what. Like here, usually can be a verb, but then context also matters. Like if we're talking about trash can, then it becomes a noun. but we need to, that's why probability comes in to measure what's more likely, and then we map those probability into giving us like a final tag. A quick understanding of Markov model. I would not go too deep with it, but I just wanted to convey this concept because it's very important underlying idea on which all these tag extractions work. So like take this very simple example. Do not go to into all the the probability the scores that you see there, but think about in this way. Like if there is sunshine today, what is the probability that there's going to be snow tomorrow? So according to the model that we have, it's 0.2. So here the sunshine, snow, and rain are like three states that we are talking about. The transitional probabilities that you see are like changing from state to state. So if someone asks from you from this image that what is the probability that it's gonna snow tomorrow, if today is sunshine, you would say that's 0.2 probability. Why this is important is because the POS tagging concept is also based on Markov model, but it has another layer to it, which is like a hidden model. Now, again, with the previous example of sunny, rain, or let's just consider sunny and the weather is like or sunny or rainy. You would see here that in the image that I've highlighted, rainy and sunny is like kind of a hidden, like you do not know if it's raining. Like say you are in a very closed apartment, you have no windows. It's a hypothetical scenario. You have no windows, but then to understand if it's raining or sunny, you call up a friend and they say, hey, I like live right next door to you and I'm going for a walk. So you know that as an observation, that's your observation states that you know that your friend is going out for a walk, or if he's going out for shopping, or if he's just cleaning and staying back at home. So from that, can you refer or can you defer that what is the current environmental state today? So basically, if you see that if he's cleaning today and at home and not going outside, maybe it's raining. And from the probability states that you see with the not with not the straight lines, but the dotted lines, those are like emission probabilities. So basically, these are the probabilities that come from the hidden states into your observational state. So basically, there's like kind of 0.5% probability that if it's rainy, your friend is going to be staying home, cleaning, and not going out. So you must be thinking that how it applies. Here's the logic. The logic is we need to predict the sequence of states that's not directly observable, but given another sequence that you know which are observable to your current environment, how do you understand or how do you refer those dependencies? The first time I was trying to understand, the major question that came to my mind is that where are these probabilities coming from? That's a very generic and the correct question. From past data observations. Look at this chart and I tried to highlight the states for the first question, like say how many times you see that if it's sunny, the next day is sunny and next day is sunny. There's like a weather record pattern that we are trying to analyze it from. So if you count, there's like 8 states that if today is sunny, tomorrow is going to be sunny. So that 8 state from sunny to sunny becomes your 0.8 probability that if today is sunny, what's the probability that tomorrow is also going to be sunny, according to only these few observations, not everything, but this is like a sample use case to it. So how is POS tagging and HMM related, right? Like why are we discussing hidden Markov model? We need to understand here that for the computer, the observable states is the word in the sentences. Like it has all the words that we are passing to the algorithm, but it does not know what are the hidden states, which is like the POS tags here. So we need to estimate those POS tags using hidden Markov model. So like we say like we are trying, so the first method we're trying to understand what are the possible tags, calculating that given a verb, the next word, this is a very basic conditional probability domain. Like if this is a verb, predict that what's the next word, it's going to be a noun. So in the same way, for the final, the next stage of it, where we're trying to, get all the emission probabilities from the hidden states, is like given a tag, like say a verb, it's associated with the given word, say running. So that's the final layer of connecting the word to the tag for the probability mechanism to give you a score and say, hey, running is actually a verb, because we have seen in the previous data set that when running like when running comes up, it's termed as a verb, and we are doing a count of how many times running is termed as a verb, and also a count divided by the total number of count of verb in a particular document. So if you want to, I'm not going to go too deep into all these, mathematical equations, but if you want to explore more, do refer to Vertify algorithm. You can look it up. They have like full explanations of how peer tagging and HMM is related, and you can go and understand it step by step through it. I have noted the sources down below in each of the slides, and you can refer to them on your own time in the later stages. So yeah, I think I spoke a lot, and that was a lot of concepts. So it's like a good time, I guess, to take a few deep breaths, and we're gonna go to the next part of the presentation. So please do ask any questions if you have, and we're gonna try and answer as much as we can. So next is shallow parsing or chunking. So this is kind of maybe a middle ground, I would say, that it gives you enough information about the syntactic structure to reliably kind of extract the meaning from the language without going burdening your system like with unnecessary information. So it is also very helpful in terms of utility and speed with respect to say, so POS tags are kind of like tokenized, and it gives you very little information versus like full parsing, which gives you like a lot of information. So if you want to be like, understand the overall meaning quickly with speed and not too much of memory burden, shallow parsing or chunking is the way to go. So it's basically a process of dividing the text into syntactically related group. So in this example, you would see that we saw the yellow dog. So we is like a preposition, verb, and then adjective, and then noun, everything together. But the next step of it would be to group it together, chunks of POS tag that make sense together. So the yellow dog then becomes a noun phrase. That's how we are combining it together. We'll see how. Then the understanding is that the segments in label have multi-token sequence, so it's very crucial in terms of information extraction when you're trying to kind of create subcomponents as locations, maybe name of the person or name of the city. Imagine it like the United States. If you tag it separately, we'll see the example when we go over it in the code section, but it'll in the POS tagging section, it'll be like individual tokens, but when you do a noun phrase, it'll come together as the United States of America. Great. So POS tagger versus chunking, like I just mentioned, POS tagged is like very individual word based, tokenized based. But when you look at a chunked tree, you would see that it's kind of noun phrase. The cat becomes the noun phrase. The little yellow dog becomes the noun phrase rather than keeping it word level tokenized. We spoke a little bit about constituency parsing the other day, but I just wanted to give you an understanding that this is one level, again, higher. Here, what we're trying to aim is to extract a tree from a sentence that represents its structure according to the phrase structure grammar. So you can read it up. There are a lot of work that NLTK has released, and still they're trying to like make it as accurate as possible. And sometimes the applications differ based on the use cases we have at hand. But the next one, dependency parsing, is kind of very useful. Like we see it in some of the code applications as well, that it's, what is it basically? It's like kind of a task of extracting dependency parts of a subject of a sentence and trying to see that which head word, like which head words kind of have a relationship with other head words, right? So if you think it from the chunking thing that we were talking about, like say the United States of America, if we try to parse it in a dependency parsing methodology, then the United States of America will all show you these kind of relations towards it and say that it's a compound connection with the previous word. So the head-to-head relationships will have compound connections, which will tie and kind of create the final noun phrase for you. So it's kind of another methodology that we can do this. Great. So this is the last step of it. I wanted to keep this is a great representation of how we are giving the raw text or the string to the algorithm and what are the final output that we're expecting. So here it's a step-by-step process that you give the raw text, which is a string. We do sentence segmentation, we get sentences. So it becomes a list of strings. Then if it's a paragraph, and then it becomes list of sentences from that paragraph. We tokenize it. Then tokenization sentences also have like a list of strings, which is like gives you the final part of speech tagging for each. From there, we can do entity detection, like for the previous example, when we have say achieved the noun phrase of the United States of America, that becomes an entity, right? We're going to see what entity means just like a little later. But the next step of it is like understanding the entity detection and then understanding the relation between multiple entities, so that we can kind of create a knowledge base or a knowledge tree of all the information that we are passing, and that's how we're going to analyze the text and make sure that our model works. Great. Okay, I guess if you have any questions regarding any of these methods, we're going to be available in Slack as well, or you can ask any questions in QA section, and we can go through it again. I guess these are the stops where I take a deep breath, and if I need to, let me know. I see, yeah, I see in the chat that some of you want me to slow down. I can slow down a little bit, and great. Great. I can, okay. So to go forward with it, the next segment would be named entity recognition. Like as it's very evident from the image here, like it's a way of automatically like finding names of people, places, and organization in text across like many languages. We're gonna talk about mainly English language here, but you can do it in multilingual format. So what is NER? So here you would see that there's like a paragraph or like a full text where you see highlighted entities. So entities are basically terms that kind of have a lot of information with them and has like a unique context. Like if you see it's a person, then there is a person, there's New York Times, which is mentioned, which is like an organization, and then FBI, and then a date, a format, a person format. So these are like all the predefined classes that we have under NER. So these represent basically real world objects like people, places, objectives, organizations, dates denoted by basically proper nouns. So entity extraction, we are trying to like, kind of extract all kinds of contextual meaning that we can from the sentences. It's a very useful way to do information extraction, identify segments, and kind of map them into predefined classes. Because if you see, these are all predefined classes. We know that there is a date format, the date class, there is like a person class, there is an organization class, and we will go much deeper along with it when we go through the code. Great. So what are the steps of NER? It's basically you detect a named entity based on all the pre-processing and all the steps that we discussed before, right? Like we spoke about how we can utilize noun phrasing, how we can first tag it, POS tag, then noun phrasing, kind of doing shallow parsing, dependency parsing. So that's how we are kind of detecting a named entity. Then we're extracting it. There are a lot of tools, methodologies that we can deploy in order to do that. And then categorizing them, that which category does it fall to. So here is a great example that I really like. So like if you, this is a tool, the source is in the bottom of the presentation. Like if you open it up, you can like put any text of your choice and you can run through it, and the algorithm will give you, or the demo would give you which person or location or organization it could have, like it extracted from the text you provided. So here the tags are like companies named as SpaceX. There is a person category, Elon Musk, location, and two locations. So there can be multiple locations. I would also want to add, we'll talk about it later a little bit more, that we can also add our custom tags. Like say you have a very particular, niche data set, like maybe a legal data set, or anything that's very domain specific and that doesn't work with, the general model trainers of the NER that we already have open sourced, you can build a customized NER on top of it, on top of all these model base, so that you don't have to start from scratch. You can just keep adding on layers of information and customize tags, and then add annotated data in order to train on top of it. So what's the method of NER extraction? Yeah, just to give you an overall idea about what we can do, like what are the options, what are the cons, and like some of the ways we can do it better. So the lexicon approach is basically relies on like a knowledge base ontology. Here, all the terms are related to a particular topic. They are grouped in like, different categories. And the system also looks for matches within named entities. Some of the example would be like, say, if you have a city data set, or like a data set that has everything from city, country, name of location. So you can create a lexicon of city, states, and a country to recognize location in that data. But say a new country has formed, or a new state has formed by dividing two states, that's like new information, right? So the con is like you won't be able to extract new words that's not already in the pre-lexicon format. So that means that we need to always keep up with it. We need to keep it updated all the time. And you need to have like so much data annotated that sometimes it becomes not feasible or scalable to go via this route. But it's very accurate. If you are trying to solve very particular kind of a problem, you can definitely use something like this. There's also rule-based, like say there's a series of grammatical rules that you like have like your subject matters experts have like handcrafted it, and you can get the results high precision. But the cons here as well is that the defining of the rules takes a lot of time, because it's not like I know every information that's out there and I can like kind of create a rule for everything at one go. It has to be in a iterative basis, and that is takes a lot of time. And it's also very domain specific. So like any general data scientist, like if I'm working on something and I do not have domain knowledge, I would not be able to achieve good results with that. So an example is that if you want to build a model to extract, legal terms from a document, you need to manually tag some of those documents, like that talks about the specific legal methods, maybe cases, process, or terminology that maybe we are not aware of in a very general use case scenario. And there's also machine learning based system. So what you can do is that build an entity extractor. We feed the model with large volume of annotated training data. Here, as this is like a general problem in all machine learning problem, or supervised machine learning problems specifically, that we need good tagged, good annotated, and clean training data in order to start building a very reliable model, be it core machine learning or NLP in every scenario. But at least this makes like, or gives us the opportunity to start step by step. Maybe you can bring in human QA at the middle of it, and then kind of go or build it from there. So let's talk about a industry use case of NER. You'll be like, oh, this is great, but how do I use it? Or what are some of the real life applications that these technologies are getting applied to right now? So if say you talk about a problem that's like, if you want to reduce the time for processing customer queries and tickets, like you have you have a website and people are raising problems and queries. And the goal is that you want to increase customer satisfaction, definitely, by reducing the queue time, and you want to solve the problems faster. And you also have constraints, which is like you have limited number of agents who will be able to respond to those tickets. So you want to kind of like minimize their burden. So what are some of the steps that all these methods of natural language can give you a good start or a good push in order to make that system a little more seamless and faster? So here comes entity extraction. What you could do is, the idea, like if you want to look at the example here as well. So here the goal would be, what the natural language process can help you in a way is like to extract maybe the key terms. You have built a model in order to know exactly what your business use cases are, what are the, say, the product names, the business use case names, or if it's something very domain specific. And even if they're like, say, a lot of time we Google for error codes, right? So like if a customer says, hey, in your website, I'm constantly getting this error. What if you already have a categorized, a cataloged error sheet saying that if you get these kinds of error, you should refer the problem to this department and they can handle it out. So if those kind of entity recognition already happens, it kind of gives you an easy way to, assign a ticket to a particular department. And rather than, the agents coming and reviewing them manually and saying that, okay, this problem goes to this department, this problem goes to that department. So it kind of streamlines the first level of manual QA. Great. So the training of the model, this is like a very generic, kind of a representation, but it kind of gives you the feel of what we are trying to achieve. Is that you have a dictionary where you have all your use case data, your particular business domain data, you have input documents that are coming in the previous example that was like the user queries or the user complaints that were coming in. You do all kinds of pre-processing, like you tokenize, sentence splitting, POS tagging, lemmatization, string normalization, etc. So now you're trying and doing entity annotation, like we need to understand how, which, or extract the entities. For that, we are doing multiple n-gram. We're going to talk a little bit later about n-grams as well. Say string matching, does it directly match with some of the already tagged data in your database, and then you can match it back and directly pull the results from there and say, hey, we found a match for your question. Here's some of the links that you can refer to, or if you want to talk to someone directly, from your that particular domain that can help you, and we will route it through that domain members. And then the post processing would be like relabeling, creating some of the rules, and then the final output would be that you would get an entity name and a type, and we'll see how. There's this tool, I found it very useful, like we kind of used it in some of our initial work use cases. It's that Prodigy unfortunately it's not yet open source, but this is kind of a very user-friendly UI, I would say, where you can upload your own data set. It will do the initial tagging. Like in this example, you see that it found Nintendo Switch as like kind of a product, and you have the the final call to say that I accept it, reject it, or you kind of ignore, like, or change the tags accordingly. So for any kind of business use cases, if you're working back at your work and you need a good or a clean way of tagging, I would definitely suggest, but unfortunately it's not open sourced yet. So they have some fee to how they work through it, but it's a great tool though. Great. So yeah, I spoke a lot again. Think about some of the concepts we discussed. If you have any specific questions, definitely ask or write it down. We can address that later as well. Great. So this is like kind of like a big last chunk that we would discuss today, which is like n-grams. So what are n-grams? N-grams is like, it's a model where we're kind of trying to find what is the probability distribution over word sequences. What I mean about word sequences is that when you have, say, this sentence, this is big data AI book, what are the unigrams? Like, if you, without doing any n-gram, if you just tokenize it, or you just word level tokenization would give you, this is big data AI book separately as one word each. What we're trying to achieve here is trying to understand what is the probability of word sequences happening together, or kind of, you can explain it's like co-occurrences of multiple words in a sequence. So bigram would give you like two words together. So it says that this is or is big data. So every two words together, first, second, third, fourth, like that. And for trigram, it's like three words together, same as what bi was. So why would we do that? So basically it means a sequence of n words that's there, and we are trying to cut out some of the noise from the data. Like, if think of a scenario where you have to consider all the tokens that you have found, and it's like a huge corpus. It's going to take a lot of time to analyze and to go through each of it. So instead of that, what we can do is that kind of make our corpus more tight and make it more relevant, so that we only keep those n-grams that like occur a lot of times, comes through as like a very strong contention, and then we can start our analysis, and it'll give us like a kind of a very clear theme. We'll see some of the visualization in the code section for that just looking at that, or maybe just doing that quick analysis, you would find that what are the top, top terms that people are talking about? What are some of the top areas that the whole text consider or like refers to, without kind of reading through the whole passage, or maybe like a whole document sheet with like unigrams or like word level tokenizations. So the applications include like, speech recognition. We use it like for a lot for machine translation, and also predictive text input. Like if you need to, predict what's the next word it's going to be, n-grams also play a big role there. We're gonna have a quick overview of this. Like think about it like a probability of word that, and given some history of that word. So what's the probability that a word will occur? It's like again conditional probability at play here, given the history of how many times it has occurred together. So here let's take an example of the whole thing is called today the sky is so clear that. That's the history, that today the sky is so clear that is like together has occurred, and we have a count of that from our corpus or the data that we are going through. And here the word that we're trying to predict is the. So basically what we're saying here in this whole equation, that we're trying to understand what is the probability that the will follow the H word. That's today the sky is so clear that the next word would be the, like I said, next word input prediction. So approach one is like a relative frequency count, correct? So we have like say a big, large corpus. Corpus is like a chunk of a big data that you have at your disposal. What you could do with that corpus is that step two, you take the number of counts, like the times today the sky is so clear that appears in that corpus. And then you take a count of number of times that it's followed by the, right? So it's basically just clear case of understanding how many times the co-occurrence of these two H and W have occurred. So kind of you're creating the probability of, given that today the sky is so clear has occurred this many times, what's the probability that the will follow it next? So yeah, what we're trying to answer with this this mathematical approach is that out of times you saw the history H, how many times did the word W follow it? So like I mentioned, the use cases and the examples are a lot in like say a question answering domain, next word prediction, and also a lot in information mapping. But as you can see, there are some of the cons of approach one. Like if we have like say a huge corpus, approach one needs to go over the entire corpus in order to do that frequency count or counting through each of the words that we're trying to predict. It's kind of not feasible, and it's also tight on time performance. So what do we do? So we decompose the probability function into smaller chunks, kind of not take it to the whole individual sentence, but kind of use it via chain rule. So what we are suggesting here as a solution to cons of approach one is that instead of computing the probabilities using the entire corpus, why not create like a chain rule using n-grams and approximate it like from just a few historical words that we have seen have occurred most with the. So we kind of saying that let's not think about today the sky is so, like we're not at all worried about these individual words, but let's consider a very few historical words that have occurred closely with the. So that method is kind of like the approach two, which is like the bigram model. So here we're kind of approximating the probability of the word given all the previous words by using kind of like one conditional probability. So yeah, don't get like deterred by the big equation here. What it's basically trying to say is that we're trying to predict one word, which is WN. If you say here, if you see I've mentioned that WN that we're trying to predict is the word the. H is like our history, which we are even not considering in this whole approach. But what instead we are considering is Wn minus one. That is the penultimate word before the, which is that, right? So here we are assuming that probability of a word depends not like kind of only on the previous word and not on the entire sentence that it has in its prior section. So that's the Markov assumption that we also saw it a few minutes back. So if you want to wrap that up, what it means is Markov models is kind of saying or assuming that we can predict the probability of some future unit, example, the, without looking too far in the past and just understanding the very penultimate chain that that future unit is connected to. I'll repeat that once again. I know that was like a lot of words in a explanation. So basically, we are not consider like when we are going step by step approach, we are only considering what was the closest connection units rather than going back to the whole corpus. So it beats, so it helps us in reducing the time, the resources, and also the scalability issue that we had with the previous approach of doing through entire corpus. Great. So I guess we this is the NLP workflow that we are kind of going through today. The text representation and feature engineering space is a big space where there are multiple ways that we can feel like help or uh, make the text better for in order to be able to make a model that's like much easier to achieve the goals that we're trying to. uh, the theory and next steps is that we spoke about syntax, semantics. There's also shallow parsing, chunking, part of speech tagging, named entity recognition, and engrams. So these are, in itself, these are a lot of big domains. So if you want to focus on one part of it, I would recommend go step by step, like maybe start from understanding and clearing some of the baseline concepts, and you can build on top of that with each of these domains. And we're always here, so ask if you have any questions. So before we go into the collab, I guess we're gonna take a quick, let me check quickly what time it is. It's 3:50. Let's take a quick 10-minute break and we're gonna come back. Sorry, it's 3:50 here, EST time. So we're gonna take a quick 10 minutes break and come back after 10 minutes. So you guys also try and go over it a little bit and take some water maybe. And we're gonna see you 10 minutes later. And thank you. And please do ask if you have any specific questions. I'll try and answer as much as possible. Hi everyone. Hopefully you guys took a good 10-minute break and maybe had your water, coffee, tea, whichever works. Uh, so so I understand that was like a lot of theory that we had to cover. Since this is a deep dive, we wanted to cover the major areas of feature engineering and ensure that we have like an overall idea. I would encourage you guys to maybe in your own time like look through some of the resources that's already there as in the slides as the source links in the individual slides, and like get back to us if you have any questions. Happy to help anytime. But in order to get that whole understanding of what we're trying to achieve, it's very important to like understand a little bit of the baseline math, and then just go and try a hands-on implement. The more you do hands-on work, more clearer you will be in where or which areas, if you improve, what changes. So great. So we're gonna look at the Google Colab notebook. I hope all of you were able to download the link. It's here in the Women Who Code Data Science. So before I go ahead, I would also want to ensure that all of you can follow and upload your link from the Google to your Google Colab. So if you go to Google and just type Google Colab, the first link you get is the link that you want to click to. Go there. You would see you have multiple options. So you click GitHub, since you already have the link from the Women Who Code GitHub that I'm sure have been shared in the chat. You can go click the GitHub link there, search, just quick enter, and you will see that there the list of all the notebooks that's available in that repository pops in. So just scroll down and maybe select this one. That's the Intro to NLP 2, NLP Deep Dive 1. So if you click on that, it's going to open up in a Colab environment, and you can easily access the data set. So great. I already have one tab open, so I'm going to just close that out. And great. So if you some of the concepts that we discussed here, we're gonna try and do a hands-on implementation. Oh great, I see that someone wants to go through the Google Colab again. Sure, I can do that quickly again. So if you just go and search for Google Colab, the first link that pops up is Google Colab. You see multiple headlines like examples, recent, Google Drive, GitHub. So we want to use GitHub. You go click on the GitHub section, go back to the link that Helena must have shared. That's the link to the GitHub repository of Women Who Code Data Science. Click on that, copy that link, go back to the page that you just opened up, paste it in the search bar, and just do a quick enter. You would see that in the master branch here, you can see that this is the repository, data science, and this is the master branch. You would see all the IPOMB files that's available there. You kind of scroll down, and this is the file that you would want to open for today's second part of the session. It's called NLP Deep Dive 1. So you can either click directly on the link or click here, which will open a new, a new tab, and basically you're ready and good to go. Great, I hope that was helpful. We'll just start and go through it. So today we're going to be using a data set from Kaggle that has, a list of articles or news articles, almost around 50,000 articles. They had multiple, I guess they had three data set. You can use all three, but for the sake of simplicity and quick runtime for this session, I am using only article 1 CSV. So you can follow the dataset link here. The name of the dataset that I'm using in the session is articles1.csv. The description, as it mentions, is it's a news article from 5 American publications. How you can or what you can do, I try to clearly write it down that how you can download or upload your data. So once you have downloaded the CSV file from this link, it'll be in a zipped format. So you just unzip the file, you save it in a folder, maybe your desktop or your document section, open this Google Colab, which is already open. just go to this section here in the left-hand pan. You would see that this is table of contents and this there is files. You can just quickly upload here. This is the upload. It says upload to session storage, right? So you can just upload from your computer where you have saved the data in the previous step and just upload it here, and it will be ready to be used in your any analysis that you're going to do next. I also wanted to highlight that if sometimes like when you have uploaded the data and you do not know which folder inside Google Colab that data is there, so what you can do is use this function called PWD. It's kind of basically gives you the current repository or the current folder that it's referencing to when it's trying to get the data. So it gives me content here. Now, if you want to see that what are all the files that exist within that folder, just do ls, which is like a list command, and you see that our articles1.csv is uploaded there successfully. So now we can say that we're good to go, and we won't have any file not found error in the next steps. I hope that was clear. We can go through that later if you have more questions about it. So here, even in the the last hands-on section, we worked a lot with pandas. Pandas is a very useful library for all kinds of machine learning problems, and so for NLP here as well. So I tried to keep all the nodes, all the code blocks have like a common section. So if it's not clear, do let us know. So here, basically, we are reading the CSV file into a pandas data frame. We are just using .read CSV and utilizing that link that we found, right? Which is like a, just put together the path and the file name. So the path is /content and the file name is articles1.csv. This step, we are trying to get the shape, sorry about that, the shape of the data set that we just loaded into our data frame. So for me, I actually really like keeping my, what do you call like the value or the name of the, that just went out. What is it called? The name of the data frames that I use for reading each of the documents. I want it to be very descriptive so that in the following process, I know exactly what I'm referring to rather than just using DF or however it works for you, you can do that. Great. So here in this step, we are trying to see what's the shape of it. And I'm here in a quickly printing it that there are say n rows and n columns. So you would see that here when I'm printing the head of the data frame that we just loaded in, it says that we have 50,000 rows and 10 columns. So we can just review kind of and have an overview that what are our fields we have working here. We have like an ID, a title, a publication, author, date, year, URL, and content, etc. So you see here in the first CSV file that we loaded into the data frame, we had an unnamed column. So this is not something that you have to do, but I just wanted to keep it here so that we are aware that if you want to drop a column, maybe how to do that. So you can do something like I'm using the same data frame. So basically I'm saying that news articles df dot drop and column 0. So column 0 is our first column here. And you would see that I'm using a tag here called axis equal to 1, which means column wise operation. If it would have been axis equal to 0, then the operation I'm saying that would be row wise. So now we are doing shape again to see if anything changed. And I see that it says news article shape is now, it has 9 columns. Great. So kind of, so if you see the difference, we kind of dropped the unnamed column, which was like kind of, I guess, a plain serial index. So now we have ID, title, publication. So before going into any kind of analysis, I just wanted to do a little bit of EDA, which we already covered last week, how to do a described data. So you do, when you do info, you kind of get how many null values are there, what are the data types, if it's an int, it's a float type object, or it's like an object which it kind of refers to that it's a pure text or a string based column. Great. You will also see here that it kind of sums it up for you that you have 3 column that is float type, 1 column that is int type, and then 5 column that's object type. Now, I guess the next step is to see if we have any null values. So getting null values and seeing and to, like summing it up kind of gives us a picture of how many missing values we have in each of the columns. So you can do it in a very simple way like this. Like you call your data frame and you ask that is null function, and then you do sum. So what it does is kind of calculates how many missing values it found, and then it sums it up together to give you in a very clean format so that you can easily connect to it. We see here that author and URL is kind of like the areas that we have you know a lot of missing values, but I guess like for our use case today, it's not a big worry for us because we're not going to be using those columns too much. But if we were, we would like find some ways of filling on those missing values. So for eating of the day set, I want to like really reflect upon that Matplotlib is like a great you know what do you call, like a visualization library, and we need to, it gives you like many different kinds of variety of charting your data accordingly. So what we are trying to do here is like kind of doing a count of how many publications or unique publications are there that is referenced in the data. So what we could do is that we just do very simply, we just do rest everything that you see here is kind of heuristics to make it look pretty, but without that even you could easily do the chart. So what you're doing here is like plot x level as publications and then y level as counts. So we're, these are the name of the the x axis and the y axis that we're naming it so that we can easily explain the charts. And the final step of creating the chart is here, is like you're calling the data frame that you just created, you're calling the publication, which is the name of the column that you have within that data frame. You're asking it to have like a value count. So basically it counts up unique values in that whole publication domain. And then you're saying that, okay, create like a bar chart for me. You're plotting that bar chart. Here, what I did is that I wanted to keep it like, a little difference in color so that we can like see the different domains clearly. So I just mentioned that color list is like this RGKBMS, which is like red, green, blue, whichever. You can even do it without that. And this is a very standard way of keeping the plot figure 10 to 10, 7 so that it's like, clearly visible to the audience that you're presenting. So we're calling that color list here as the color. And if you do not have a color list, no worries. You can just omit this section and then close your parenthesis here. So the chart that we get here kind of shows us the count of the publications that's there in the data set. We have Breitbart, we have CNN, we have New York Times, Business Insider, and very few amount of Atlantic representation. But yeah, we are not going to be worrying about the skewness of the publication houses yet. We're just going to see how it's getting represented. So that was one. I also wanted to like explore, so these are like not very good practices to ensure that when you are trying to understand, because the best way to create the best model is that you understand the data like through and through. So maybe take the help of visualization in order to understand what are the some of the skewness, what are some of the differences it has, and then you will be able to grasp the data much better than rather not doing it. So I guess I really like visualization, and I try to put it there in everything I kind of do. So here I just wanted to see that, okay, what's the visualization of news articles count per year? So you'll see I did the same in the same way. Only other thing I did add here is like the two data frame section, date time section is like kind of changes a string format into a date format, where I'm changing the year column, which is a string format, to a date format, and mentioning that change it to a format Y, so that when I pass it, the matplotlib function is gonna identify that it's a date. Another cool thing about Colab, or I guess even it works in Jupyter, that when you hover over any of those functions that you're calling, it kinds of give you the definition. Like you can see I hovered over format. It told me a description about what's a return value type and what other arguments that I can pass in the section. Same with to date time here. It should hover, if you hover over, it should pop up. Not popping up. But yeah, that's like kind of reformatting the string into a date. And then we are naming the X level as year, and then Y level as count, and then doing the same as value counts, and we are plotting it as a bar. You see here, I didn't use the color chart to show you the differences. So here you get like a normal, and we see that the publication count of articles have radically increased starting from 2015. Before that, it was like the count was like pretty negligibly low, at least in this data set that we're working with. So 2016 as the maximum representation. So this was for year. I did a similar for month and month year together. Like, please take some time to go through it. Ask. It has similar procedures that I just explained. This is for a month, just to see that is there a pattern that we could find, that which months maybe the news that was released has some kind of effect. But if you see, you see January, February, like the initial months have like a lot of data, and then you see end months have like a little downfall. Maybe you could say everybody's like in Christmas mood and maybe less news happens that time. I'm not sure what the reason might be. We need to dig deeper, but yeah, it kind of gives you an idea. Similar for month year as well. Please go through it at a time and let us know if you have any questions. Great. So for the next phase of the analysis, we'll consider only the title column, right? Like you saw, we had so many 9 columns that we had in the refined data frame. I created a separate data frame called title.df by only calling the title column from that. When you call it from a different data frame like this, title df becomes a different format, which is called as series. And that's why I needed to transfer it into 2 frame. I could have done it in a different format, but I just wanted to show you that if you're calling any column from different format, you can directly, format it into a data frame in no time. So here, another very interesting thing I really like about it is like when I want to show maybe a list of values in my data frame, I don't want to be calling head or tail all the time. So you can very quickly do like a sample, and sample of 10 would give you, and you can put a random state of 5. You can keep this constant for rest of your analysis so that you see the same versions. It just gives me, not the extreme results, that like not the head and not the only tail, but also like, a randomized version. So it gives you a clearer idea, and it sometimes helps in detecting some anomalies. So another thing I wanted to do quickly with, like, just to see a title length. So you could very clearly, you can just call the title or transfer it in, because it's like, data frame object. So you can call it as a str, you find its length, and then you plot it as like a histogram. So you would see that most of the titles have like, title length, maybe maximum is within 50 to 100. So that's a good way of understanding that title should be short and script. Great. So for part of speech tagging, for the previous session, Rishika did went through a lot of it. So I will not go too deeply with it, but we have used like the similar methods that she have explained in the previous process. We are downloading NLTK punct library. We are downloading the average perceptron tagger, which is like kind of the baseline in order to ensure that the POS tags works correctly. For contractions mapping, importing the similar libraries, and we are doing the first construction fix here. So now when you see that we had, so once we apply the contraction fix and do the word sentence split, you would see the final result would give you like a tokenized format, because now it's clean. An example, if you go up, you would see here that it says, oops, I cannot see it, but then there was multiple some of the, let me see, maybe we'll find it in the later stages. But these are like now all tokenized, right? So I wanted to bring it back together into a particular sentence, because I'm going to do some other analysis that would help if it's in a full sentence format and not in a tokenized format. So I'm just doing a join map. So what this function does is it calls each of the word inside title df title. So it will call individual words like privers, urges, GOP, and then join it with a space between it, and then push it together as like one string instead of like a list of items, so that it's easier for me to do the next steps of analysis. Now you can see, so the next step is like, also I wanted to just highlight, if you want to, dig deeper and see individual cells, you can just call the cells like that, maybe call it by their, some of their, slicing values. You can call 0 colon 10 and it'll give you top 10 or however you want to. And then you can also look at some of their type functions. So for cleaning and the spacings and special characters, I really the regex or regular expression, as it is called as a full form. I'd really encourage you all to like go and read about it. Regex is like a lifesaver in a lot of NLP problems, because sometimes the inbuilt tools misses something, but you know how, if you know how to create like a regex for your particular use case. Like one time I had to create a regex to only, extract phone numbers, so it gets very easy to detect that in sentences and uh, extracted for use cases. So here I'm just doing str.lower, everything becomes lowercase, and here I just am applying the regex that I've created. I've also given a quick explanation of what each of these WDS means. So it's like, if you can read through it, W is like it's matching any word that's equal to either like both lowercase, uppercase, and the numbers. D is like it matches digits and everything, and it kind of gives you, a clean format, and you see that all the extra special characters have vanished. Great. So for NLTK tokenization, again, like we saw last week, we are applying the word tokenize that we called from NLTK a few steps above, and we're creating another column called tokenized title, and it tokenizes it very, very, very clearly, effortlessly. For stop word libraries, there was another very interesting application I really liked before removing the stop words, if you may. This might seem a little daunting, but it is not, trust me. So what we are doing quickly here is that we are splitting the text, we are turning it into a list value and kind of collecting or counter. This is a way that we are, kind of calculating or counting how many stop words or what are the biggest stop words we had in a headline. I think it gives you a perspective of what kind of stop words you are using, because sometimes removing stop words without understanding if it's good for your use case is may get you into trouble. So always like understand what are the use cases, what are your final results that you want to get, and the stop words that may be there and can kind of help you even if you do not remove it. So here I just wanted to plot what are the biggest stop words that we have in our title section. So we say that we have the, to, in, so like all kinds of articles and prepositions, which make sense. And I guess there's nothing, too big that we should be worried about. And so we go ahead and, oh, great. So before that, I also wanted to like showcase that what are some of the, top non-stop words, words that came up. So you can explore a lot more of this analysis in this blog. The link is also in below of this Google Colab notebook. So what I did here is that similarly, like I counted here, all the stop words that's there, you can do, if the word isn't stop, you're kind of creating a +1 counter. Here you're just doing the opposite, that if it's not in stop words, then you are doing that counter. And then we are showing like the top 50. You would see that this is a slicer of top 50, and we're showing it as in a chart. So you would see Breitbart is like top. I guess it makes sense because a lot of the articles like they publish, they first talk that Breitbart thinks this, and they start from there. So that's like a big word. Then there is New, there's New York, there's Trump, there's Hillary Clinton, Obama, and all kinds of good keywords that gives you a perspective about, even from seeing this, you understand what's the general idea of all the articles it's there, and what are the keywords that they're talking about. Great. So now we go forward, and now we are removing the stop words. So removing the stop words is similar as we saw last week. We're applying, passing each word for word in X where word is not in stop words, which we define from NLTK, and then again, like I said, I also wanted to keep it like, the clean version of it is as a very sentence level, not as like a tokenized level. Like for the second counter that we have tokenized title, I created like another column called tokenized title join, and just joined it like we did before. We'll see why we did it in a later visualization. So yeah, this is just basically, cleaned up text or cleaned up string with no extra characters, no special spaces, and no stop words. So it's just key terms per each title. Great. So for the sake of simplicity here, I'm just only taking 10 titles. and just the same random state 5. So you're gonna give the same state as 5. Now, so this sentence that I passed through the tagger, the first one, it came up after getting tagged in this way. So you would see each sentence, the 10 sentences have been tagged. Say a noun, it's a noun, there's a verb, there's also, prepositions, adjectives, and each of these has been tagged. Now you might say that, okay, so I now I have tags, so what do I do with it? What insight can I get from it? So everything that we're doing, the end goal is to get insights from it and not just for just applying it. So I really like this website. They have this package called Yellowbrick. They are constantly developing, and they just also released a new version a few months ago. You can go here. It's kind of a POS visualizer, and it gives you a lot of insight into the data that you're handling to see, does the data have a lot of nouns, a lot of verbs, what kind of big chunks you can find, right? Like it gives you a heads up into your data format. So you download it by pip install Yellowbrick, you create a visualizer, and you're just tagging the tagged data that we tagged here. For each word, you're tagging the, the tag sets that we have here, and you're just passing that here. And look how beautifully it represents like how many number of nouns it has found. So it makes sense, right? Like you'll say, oh, I am dealing with the title format or title data of a news article. So noun like dominates into the corpus that we are dealing with. Then there's also verb, and there's a lot of adjectives, prepositions, not too much representation of other formats of POS tags, but also a lot of digits that have been found. Great. So I really recommend you guys to go back, read some of the documentation of Yellowbrick, and go through the code step by step. Please get back to me or to the team if you have any questions. I just wanted to keep this here. This is from the NLTK org book. This is like a must-read book for all, and like people who really like NLTK or NLP starts from there, because that's where it all started. So yeah, that's like a universal tagger framework where like you have adjectives and everything in a different connotation. So quickly, I wanted to also go through like shallow parsing and chunking. So how it differs, like maybe you remember we had like all these tagged in a previous section. Now see how the differences would come in versus POS tagging versus shallow parsing methodology. So here we're kind of creating a pattern. This pattern is very you can create your own pattern. That's why it says that it's very um, use case based, and you can create your own formats. So it's it's very intuitive to the use case domain that you're trying to say. But here what we are mapping is like, say we're saying noun phrase is something that will have a determinant, will have an adjective, and also have a noun followed by it. So we'll see if we can use regex parser, which is like another very good method that you can call within NLTK, and pass the pattern, and then see that how it gives you the format. So like say if you see that Hillary here and Clinton was not together, right? Like Hillary was mentioned as like a adjective, like in some other connotations maybe, and Clinton was like a name, definitely a name phrase. But if you see after passing it through the grammatical pattern that we created here, what you get is like kind of a noun phrase here. It says it combines the two separate POS tags into one shallow parsed chunk that would give you a better idea. So now if I look at it, I won't be confused that, hey, why is it like Hillary is turned as objective? Because it didn't find enough context in order to tag it. But when we are creating that context in the grammar, it's finding a great representation and representing it as a noun phrase. Similar for, look here, similar for New York. Look at this example. So Goldman and Sachs were like different, like one was noun, one was a verb, but when we created that grammar, it gave you a noun phrase consisting of this whole chunk of words. Great, please go through each of these examples. You can play around and print out more examples and investigate how that works out. So we yeah, so I just wrote down here the description here, like you would see in the first case that we see here. Rhines and Pribus was a different noun, but when we did that, it kind of came together as a noun phrase together because it's like a person, the name of the person was the name of the former White House Chief of Staff. Great. So we work a lot with NLTK, and I want to also introduce a little bit Spacy. Spacy is a for all of us that work in this domain every day. It's a blessing, I would say, to have some kind of this kind of an open source available for so much that we could do here. So in order to do this, you would have to do this in a two-step format. You just pip install Spacy, and also install the Spacy download and core WebSM, which is like kind of the English language model that Spacey has in the backend and kind of utilizes it for all the tagging and everything going forward. So how do you import it? So you say you import Spacey. NLP is just a event that I'm creating, and I'm saying that, okay, Spacey.load and core WebSM, and that's gonna load it inside NLP. So then if you map it out, like you print it out, what is this value as, or what's this variable represent? It's kind of say that it's a Spacey language English, which is like a kind of a model. So it's going to refer to it for all the rest of the thing that we're going to do. So we talked about dependency parsing. I really encourage you guys to go and look through Spacy. They have a lot of good way of representing the text, which is easier for everybody to look and understand. So what I did here is that I wanted to take only 5 sentences. I took a sample of 5, and in that loop, I'm calling those 5 sentences, and I am displaying that how that sentence looks in a dependency format. So few of the methods here is like the style. It's like it will show the dependency format, and I did a Jupyter true because it's going to be rendering here in a Jupyter format. Or if you don't want to render, you can also serve without instead of doing dot render, you can also serve, which will serve it into an external link, and you can open that web server up. But everything is written in a great detail in their website, so do go take a look at there. So if you quickly take a look at what this means, this is like we discussed before, it kind of creates that the connection between multiple words or multiple tokens that we have. So you see very clearly that rents and previous, like it shows that there is a compound relationship between these two. And urges, it's tagged as a verb, but it has like it connect, it's like a subject verb connecting to these two compound nouns that we have together. So it kind of clearly admits that this person is urging. So this is like a kind of subject, and this is a verb, and then this is like the object that that the verb is referring to. That what do we want to do? We want to build unity, or yeah. Unity is another noun, but it also has a compound. So we need to urging to build the GOP unity, which is like kind of the compound object section or fragment of the whole sentence. So it's very intuitive, like you can go through each of these images, and it'll give you a very clear idea about how the grammatical structure of the word helps us in understanding what's going on in each. So I printed out like 5. You can go through each. Maybe we can take a look at another one. You can see there's so Goldman Sachs CEO. So you again see that we're trying to map the relationship between multiple, so policy and ordered a policy. You see that there's a relationship between that you're ordering a policy. Maybe it's not the next word in the sentence, but then it has a connotation or a reference to that word tag. Great. So you can also do noun phrases that we discussed above with NLTK. Similarly in Spacey, I printed it out here. It says that the sentence is this, and and basically what we're doing is we're calling this function, which is very simple and intuitive. We're calling noun chunks. It's all inbuilt within Spacey, and sentence doc is nothing here. We're just passing the sentence that we have, which is this full cleaned text that we have, into the NLP method, which we just initiated above, a few cells above, which is like the Spacey English language model. And we see that once we call the noun chunks, we're printing it out what those noun chunks are. And from this whole sentence, we are getting Ryan's Privers, GOP Unity, and Trump are like some of the nouns that has been extracted. It's really useful, right? Like you want to be understanding what the context of it without understanding or without like manually reading through everything of it. Same here. Uh, Great. So for verb phases, I wanted to introduce another library. It's not mandatory to know definitely, but they do have a lot of use cases. You can just download, pip install Spacy, and you will see that again, for a similar pattern that we discussed above, what you can do, like take maybe a sample 5, and then if you call make Spacey doc, you are currently calling the ncore web sm, which was the um, which was the Spacey method English model language, and then you are trying to extract the verbs that matches the regex pattern. So this is the pattern that we created, that we want verb, adverb, and verb in that format, and we want to extract the verbs that exist between these formats. So once you do that, I tried to print it out, and then it says that, okay, in this sentence, it says that report 97% of DOG employee political donations, and report is like a verb, it's like reporting, and then it went, like I went, it's like all action words that make sense, right? Like urges is also a verb, like I urge you, it's like an action token that I'm referencing to. You would see that there are some of the warnings, but don't worry much about them. They're just there so that we know that there's also another method that could work. So you can try replacing that and see how that works. Great. So we covered a lot. We went from, you know, data cleaning, visualization, basic EDA. We also looked at tagging, part speech tagging. We did shallow chunking, parsing. Sorry about that. Next step would be to understand the named entity recognition, and Spacey is infamously famous in this domain. I guess they do a great work in capturing some of these very general use cases for us. So you see how beautifully they have kind of tagged or highlighted the areas that for each of the sentences that we are passing. So I printed out, so what we are doing here, again, we're taking sample 5 cases. I printed out the sentence just so we know that what is the final sentences. There is, and then basically fit the sentence into the NLP English model, and then sentence doc becomes the object. And we kind of rendered that object with an ENT. So ENT is the style is because it's entity. For the previous one, we used DEP, which is for dependency, right? And then Jupyter for true, and it'll give you, so what kind of already pre-tagged use cases that it found. So it found org, GOP as also an org, New York Times also an organization. It also found 97%, which like kinds of maps back to a person, and then it found Hungary, which is like a GEP or like a location based, and it also found person. And you see the best part of about this is that because it's parsing based on the shallow parsers or the chunked and not the individual tokens, you would see that you get the whole Hillary Clinton as like one person, name of a person, and not necessarily breaking it down based on tokens. So yeah, even for Madeleine Albright's Goldman Sachs comes up as like an organization. So it kind of very intuitively gives you a like an understanding about what are the kinds of information you have in your data, and maps it out there. So great. So I also want to explore that not only what we have, but how can we, measure that what are the kinds of or counts of organizational tags versus person tags we found. So for that, there's like a quick method I wrote here. Like you don't have to do this necessarily, but it just gives you a very clear idea. So what we are doing is here basically we are going through the range, and we are going through the content of it. So content, remember, like let me go up a bit. Sorry for the juggle. Just to give you the initial how the content looked. So all these while we were utilizing title, right? So title had a very brief connotation to it. But what if we want to go through each of these content that you see here? Because that's like the full article and has like detailed information. So that would give you, more information about the person, author, or the organization, dates, everything. So I just wanted to explore a little bit in that domain and give you an idea of, if you want to do something like that, you could do with any of the columns, right? But content would have much more. So I started with that. So what we are doing here is that basically we are calling the from the initial data frame that we had, we are calling the content, we're calling all the IDs so that we can see the representation of each article and what they have, what kind of NER tags they have. I'm creating the entities here. That's like I'm calling the dot text. I am also calling this is basically just to see, we'll see it in the next chart, that where that word starts, at what word count, and where it stops. So if you want to say build a custom Spacey tagger, you would want to, like, the format is that you would want to know that where the word starts, where it stops, so that you can annotate it correctly, and that's how you can build it in top of a already available Spacey model. And then we're also creating the label that it has found or it has tagged it to. I'm going through each of the text document and stripping excess documents or excess initial characters, and then I'm putting it into a data frame called frame, and then this is how it looks like. Like if you say renaming the columns, like when you're seeing the frames, it has no columns, but I just renamed it as text start NER type. This is what the Spacey model has tagged it to, and the ID just for our ideation. So you would see here that text is French, so basically French for that ID. This is a particular news article, and there the French word has started, in multiple segments. First, it started at character location 2974 and then stopped at 2980. It was also found in character location. You see the ID is the same. So that means it has been multiple times referenced in a same article. These are very nuanced things, but it gives you a lot of deep dive that you would need to do in order to build a big, great NLP model. So what I did here, again, the similar way, color list that we discussed before, figure size, we created the x-axis and y-axis labels, NER types, counts, and I basically called the NER type, which is this column. I do not want to go about any of the other columns, but basically only the NER type. I'm doing the value counts, and then I'm plotting it as a bar chart and the color list. So here you see the maximum time the NER that has been found in all the content of this data set or the data frame that we're dealing with has a lot of name of person that has been referenced to. Makes a lot of sense. Then we also have locations, we have date or name of organizations, work of art, time, a lot of it. Now, if you want to see, now say you got the NER types, now you want to dig a little deeper and you want to see that, okay, within person, what do I have? You can just quickly visualize it by calling only by, double, you can just call a segment of it, ner dot type, which is double equal to only person. So it's going to only fetch from this data set all the ones that has type as person here. So when you do that and you print it out, this is the label, X label, Y label, and I'm just plotting, the top 21. I don't want everything. It's going to be like big and my chart is going to be looking not nice at all. And for that, what do we get? So look at the proportion of news coverage that we have that represents the people that have been mentioned here. So we have Trump, we have Obama, we have Donald J. Trump. Yeah, so this is something we will address in a later part of the series in week 4, that how we can combine, connotations about Trump and Donald J. Trump, which are kind of like they're the same person, but since they have been referenced so many times in different use cases, sometimes it can get mapped differently, but it's not too big a problem, and we can handle with different kinds of word vectorization. We see Kushner, Putin, and a lot of the other members that have been named. And we also see organizations. And if you also want to see organization, similar way, just swap person versus as organization, and it will give you top 10 organization that was top 20, sorry, that was mentioned in the content of the news. You have Senate, Congress, White House. So the whole idea of doing the visualization here after doing the analysis is that it kind of give you an idea and more insight into the data. And that's all we are trying to achieve by starting with NLP in the first stages of pre-processing and cleaning up. You can also map GPE, which kind of gives you the locations. You have the United States, Russia, China, Washington, New York, America, everything, all the states that they have, name of the places that they have found. Great. So I tried to keep it. I tried to like keep some of the labels and counts clear so that it's easier for you to refer to it later on. And if you have any questions, please do get back and we'll go from there. The last part of it is definitely n-grams. We can do n-grams using sklearn. So I kind of used multiple. This might seem too many lines of code, but what we are just trying to do is that we created a function. We are passing n is equal to 2 here because, as we discussed in the the theory section, we want to segment the whole title section into 2 words each and see what are the kinds of insight we can get from there. What are the frequency of words that have mapped multiple times and see their counts. So what we are doing is there, we're taking the text, we are splitting it into a list and creating a corpus of words. Now from there, we're creating the top 10 n-grams. So in here, the value of it would go from here that I'm passing as 2. And some of these concepts, n-gram is very interrelated with some of the concept that we will cover in next session as well, like TF-IDF, bag of words, and how we can incorporate that in creating the n-gram. So I guess we're gonna refer to it once again, and if you have any questions, we can go again sequentially to answer that. But basically here, what we're trying to say is that we're gonna take the top n-gram from this text that we are passing. Text would be, each sentence from the title column. We're taking only top 20 n-grams that we found, and we are plotting it into this chart that it's kind of a bar plot where we're trying to show the bigram frequency. So your x-axis would be the number of times these bigrams have been identified in the whole section, and then the top 20 bigrams. So New York, and then Donald Trump, White House, very common themes that we see come up in this section. Supreme Court, fake news, evening briefing. So these are some of the areas that have come up. And similar for trigrams, instead of doing n equal to 2 here, you could just pass n equal to 3. It's going to split the text. Count vectorizer is one of the big domain of counting and going through the range. It'll count through the whole corpus, 2 is to 2 or 3 is to 3, and then fit it to the corpus, vectorize it, and give you a word frequency, which is like the word and the sum of the words, the number of times it has occurred. So here we are again printing out the top 20 trigram, which is like the giving you the view of so you see this is like a kind of skewed because New York Times have been mentioned so many times because New York Times was one of the big contributors in the publication. So I guess that could be one of the reasons, but this was just a sample of the data set, and you can utilize all the 3 data set domains and see how the applications and how the visualizations look like. So yeah, I guess the major idea that I want to pass through is that every NLP concept that we try to implement needs, if you visualize it in a way that it's easier for you to understand, and also the audience you want or you're trying to speak to, I guess that makes a lot of difference. And it's a great thing to include it in your daily habit of exploration of any data that you're working with. So I have put some of the references here. You can go through some of those blogs. They have the book of, there is referencing to multiple chapters, chapter 5 and 8 are referenced here. And some of the blogs that I found really useful in the whole analysis. Great, I guess those were like the 4 major part. The code is up definitely in the GitHub repo. So go through it, download the dataset. If you have any trouble, let us know. And I guess we'll go from there. Great. I guess that was everything that I wanted to share. The code and slides will be available to you guys, I guess, in some time. and please refer back to it. I would really appreciate if you could like read through some of those blogs. It'll give you more clarity on the underlying concepts of each, and it definitely helps in clearing the base and giving us like a good start. So I listed some YouTube links that you can do, like if you want to understand in deep what are the hidden Markov model chains, how it is referenced. I find this video by Luis Serraro very informative. He explains it like like I am five, and I guess I appreciate that because it made concepts very much clear. And since we are learning so much concepts every day, it's very good if we can learn it in a very simple way and then build on top of it step by step. So great. I guess we will see you next week. Please do join our Slack channel. You can post all your questions. We have a help me channel. So if you have any particular question or if you feel that something doesn't feel right, please get back to us and I'll try and answer and fix if anything needs to be fixed. And also, please do join us for next session. We are going to be walking over a lot of features that we discussed today, like TF-IDF, density functions. We need to implement it by say, like we'll implement it with NLTK Spacey, and we'll also do a lot of document similarity, and our leaders will uh, take you through that. Great. So I guess we still have like a couple of minutes. If you have any questions, and you can, I'm going to open up, I'm going to stop sharing my screen for, I'm going to pause sharing my screen and open up the Q&A section and look through if you have any particular question that I can answer right now. I see that Lisa is asking that could we address some high-level goals or practical applications after doing POS, chunking, and ER? In other words, sorry, I missed the next question. Yeah, it said, in other words, what do we do with those outputs after pre-processing, beyond data analysis, EDA? What are those outputs and new parsed phrases, prerequisites for? Like, what would, example, what would be one small practical project that uses this techniques from start to finish? Great question, Lisa. So yeah, our goal was to, yeah, so I guess our goal was to build it step by step. So that's why we are trying to refer to the concepts before, and I guess our plan for week 5 is to show you how we can build an NLP model from scratch. When I say from scratch, I mean from a very base data set and use all the applications like NLT, Spacy, libraries that we have and implement it. But as you asked, like where we can implement it, like think of a, like I can give you a very practical example that I have been working on as a project. Is like a information extraction knowledge tree creation project. So you have like thousands and thousands of data set. I remember I read a case study that because of this COVID-19, there were so many researchers that were like releasing papers simultaneously with some findings, with some inputs, and it was not very useful for everybody to sit through the whole document and read through each paragraph to understand each of the technicalities. What if we can create a custom Spacey model by doing all this previous tagging, building our some of your data that we're trying to extract from there, like create annotated data structure and customize and build a Spacey learning model on, and then utilize that for extracting key information from say thousands and millions of documents that we might have had. So that is like kind of a information retrieval, information mapping, creating of knowledge trees. I guess are kind of very useful and important use cases that people are using it, and that's why the research is constantly evolving in order to ensure that how well we can handle the nuance of the English language, right? Because you need to like really be sure that you are doing it right, but there's so much nuances, you need to do it step by step. So I guess that's why the research community and NLP have exponentially increased in the last 2 years, and we are still going ahead with so much of new information that we have and so much of power with deep learning and all that. We'll get into that later, but yeah, I guess the underlying use case remains still the same. Great. uh, Okay, I guess I see someone is asking what's a knowledge tree. I guess a knowledge tree would be, extended version of a dependency parsed package where you're kind of creating relations between multiple what do you how do you, creating relation between multiple tokens. Like say if I'm constantly talking about COVID-19, maybe I am also talking hydrochloroxine or some other drug that was a possible cure. I'm not saying cure, but creating kind of that relation so that when I know that something some word exists, I can connect it back to all the other referenced knowledge base that it refers to. So this is also a big domain of research, and it's still going on. So I guess we'll see how far we go and how accurately we can map those information as well. Great. I'll just quickly go through what questions I could answer. So I guess Ariel asks that how do you choose the ideal value for n grams? Great question, Ariel. This is something. Yes, or do you just always start with bigrams? This is something that is a very case to case basis. Like when I was working with a lot of legal data initially, when I started with bigrams, it felt that it was not capturing the answer or not capturing the insights too much. But then when I started using say trigram, I also tried four grams, but then that was too specific. Then I came up one more level. So sometimes it's very useful. That's why I always prefer to have those visualizations ready for me to see that, okay, if I print out top 5 or top 20 bigrams, trigrams, and 4 grams, which one does make sense? And once I have that general idea, so that's why a lot of it is also intuition. Like you need to know your data the best. You need to do all kinds of visualization in order to ensure that you understand it as best as possible, and then choose these values. Like some of choosing the values of n-grams is trial and error. Whichever gets you the best meaning, best insights is something that you would want to do. Great, thank you for the great questions. I also see Sulma mentioned that could I use those results like NER type to load into a knowledge graph? Thank you. So great. I think it's one step towards that way, but knowledge graph is not only NER types, it has many other useful information that a lot of metadata, like if you're talking about say a website, you have website link URL, that URL has semi mini domains, that domain can reference to multiple metadata. So definitely one step of it is the NER types, but that's not all of it. So that's why knowledge graph is very, like more grainy and more in depth. So we have to think about and include a lot more data than only doing it on the NER level. Thank you for your questions. Great. I see we're like almost nearing time, but I will take one more question if I can, and then we can keep these questions for connecting back at Slack. And it says, I guess Mariana mentions that how can we add new category to NER? For example, if I want to find some special word for certain field, for example, find word like NLP, data science, etc. in text. Great question. Definitely, I can also try and share the link of how you can create a custom model. The base of it, I guess I touched upon it a little bit before, that you have to create, a data set where you have that, the niche data that you're talking about, and you have to kind of start by annotating the formats to them. Like you say, if I have a very specific chat data, like if I have a company and I have a chatbot and I have a very technical specific chat data, how do I uh, utilize that to extract the features? That's the use case that we discussed for NER, right? So the first step would be that you have to start, utilize, annotate, clean the data, annotate it, figure out what are the sections that you want to build, or what are the categories like person, organization, which are the other categories that you would want to build, create a tag for it, and then build on top of the Spacey pipeline. Yeah, it's definitely possible to build on top of the NER, Spacey NER that we have, and you would find like ample of resources talking about it. What are the data structures you should have before passing it to the Spacey pipeline, and and it definitely works. Like it works like a charm. Like great. So this is great. I guess we are almost like time. Thank you everyone for attending the session. It was like amazing walking you all through the session. Please to ask us if you have any other question. Please join our next week's webinar, and we'll go more on much further details. Thank you so much for joining. And I really appreciate your time, your Saturday evening from whichever time zone you're joining. And I hope to see you all soon again in next session, and appreciate all your patience. Thank you.